Welcome back, folks, to another JLAM Bio video. Today for our integrated chemistry physics kiddos, we're looking at video 3-3. So we're going to be talking today about conduction, convection, radiation, and thermal energy. So what we're really focusing on today is the relationship between work and energy. And our real focus is going to be on how does energy change in a system versus surroundings. How do we get energy to change throughout all the different ways that we even use energy in life? So that's going to be our real big focus for today. So hopefully by the end of this video, you should be able to understand and explain conduction, convection, and radiation, differentiate between thermal conductors and insulators, and explain how thermal energy is used in a variety of heating systems. So we're really focusing on the practical aspect of the transfer of energy. So let's talk about some different ways that energy is transferred. The first one being conduction. Conduction is the transfer of thermal energy by collisions of particles that make up matter. So consider a pan that is placed on a stove. You know that a stove gets hot. That comes from either electrical energy or gas heat, but regardless, it does get warm. So energy is being transferred to the the top part of the stove that you put the pan on. Well, items that have greater energy, the particles are moving faster. And so if something comes in contact with that surface, then the particles in that surface are going to get faster. So when you place the pan on top of the hot part of the stove, then the particles that are inside of the pan start moving faster. And when they move faster, they get a higher temperature. Then that energy that is in the particles in the pan then transfers over to the liquid in which you're trying to boil or trying to heat up that is in the pan. So that is conduction. The transfer of thermal energy by collisions of the particles. The particles collide in the surface of the stove, which collide with the surface of the pan to heat it up, and then the surface of the pan, those particles collide with the energy that is in the liquid, thus the liquid warms up. Metals are very good conductors of heat, and so that's why lots of things that we use to conduct heat and even electricity are made of metal. Now, it may be hard to believe that solid objects have particles that move, but they do. But those particles that do move end up transferring energy through the process of conduction. Now, convection is the thermal transfer of energy through a fluid, such as gas or liquid. Warmer liquids versus cooler liquids. Warmer liquids would be closer to the bottom of the pan in this particular example, but when those particles warm up, they actually rise to the top. Warmer liquids and gases are less dense, and so they tend to rise to the top. When the particles rise to the top, they're actually going to cool down because they're not in direct contact with the bottom of the pan that is in contact with the bottom of the stove. And so those particles cool down, and as a result, they sink back to the bottom because the density of those particles increases. And this process continues where you kind of get a circulation of warm and cool liquid or warm and cool gas depending upon the system, and that involves the transfer of energy as well. If you think about a lava lamp as a great example of this, you see the lava in the lava lamp go towards the bottom, towards the source of heat. Well, it heats the source back up, and then it starts to float back to the top. When it gets to the top of the lava lamp, the lava cools down, becomes more dense than the liquid, and then goes back to the bottom. And this cycle is a classic example of convection. Now, radiation is the transfer of energy by electromagnetic waves, waves that we cannot see, such as light or microwaves. The sun radiates ultraviolet radiation. Now, keep in mind, the sun radiates a lot of solar radiation to the Earth. A lot of that actually gets reflected back out. It's either absorbed by the atmosphere, absorbed by clouds. It can even be reflected by the surface or absorbed at the surface. If we did not have an atmosphere, life could not exist on Earth. We would have too much solar radiation, which would heat the planet too much, and that amount of heat would not allow for life to be able to be sustained on the planet Earth. So radiation is just another way that energy can be transferred. Now, how do we control heat? Because that's something that's very important in our day-to-day lives. Well, a lot of the materials that are in clothes are designed to help decrease energy transfer to keep you warm. We want to keep the energy inside because energy transfers from hot to cold. And so if you're wearing poorly insulated clothes, then you're going to lose that heat very rapidly, and you're going to feel very cold. But there are clothes that are designed in order to decrease the amount of energy that is transferred and thus keep you warm. Animals have this as well. You know that lots of animals that live in the Arctic have layers of blubber or thick fat that help them retain heat in cold climates. Thermal insulators are also materials that conduct. Thermal insulators are materials which thermal energy moves slowly. Wood, fiber, glass, air are all great thermal insulators that do not allow for the transfer of heat very easily. And that's why you see a lot of building materials that are made out of this. A thermos is an excellent example to look at this, because a thermos can keep things both hot and cold for a very extended period of time. Well, how does it do that? Well, if we take a look inside here, the key thing to look at is the vacuum. In a vacuum, it's very, very difficult to transfer thermal energy. In fact, the only real types of energy that can be transferred through a vacuum would be electromagnetic, which we really don't have to worry about in terms of a thermos. So the vacuum that's there prohibits a lot of energy from being transferred through convection or conduction, thus keeping the material inside of the thermos, whatever temperature it was originally. So how do we use thermal energy in our homes and from day-to-day life? Well, there's lots of different ways that we can heat and cool homes, one of which is the forced air system, where a fan blows warm air while vents collect the cool air and recycle that process. So the vents take in the cool air and run it through either an electrical furnace or a gas furnace. And then you have vents probably in your home that emit the warm air. You also probably have several intake vents as well inside of your home that don't actually blow out air but take in air. Radiator systems are closed metal containers that circulate warm air or steam. You tend to see these in older homes on the bottom right-hand side, but these are also ways that thermal energy is transferred and used to heat up your home. And electrical systems as well. Coils turn electrical energy into thermal energy, and you see a lot of these with things like space heaters that you may find in your home. Solar heating is another excellent example. Building materials absorb solar energy or windows, so even though you may not have a solar system in your home, solar energy still plays a huge role in keeping your home warm. A lot of times when it's warm outside, the windows will be left open, and that will allow solar energy to get into your house, or you have thermal insulation. Wood, we talked about, is a great insulator. Solar collectors turn radiant heat from sun into thermal energy, so you can actually have solar panels on the top of your house, which I'm sure you're all familiar with. And these are used to convert the radiant energy of sunlight into thermal energy that can actually be used in your home. One thing we do need to talk about is thermodynamics, and that's simply the study of how energy moves. And when we look at how energy moves, we have to define what is known as the system and the surroundings. The system is basically what you're looking at. So for example, if you put your hand on a stove, the system is going to be your hand, and the stove is actually pretty much everything else in the universe other than your hand. You're just simply looking at how does energy transfer. And so if that's the case, my hand touches the stove, well, obviously there's a large amount of energy going into my hand, particularly if the stove is turned on, but also energy is leaving my hand as well, because odds are the amount of thermal energy inside of my hand is less than that of the air. Also define energy being lost by your hand from the hand to the air that surrounds it. So before we wrap up, just a couple of things about laws of thermodynamics that govern how energy is transferred from a system to its surroundings. And the first law simply states that we cannot create or destroy energy. We can only change whatever form that it is in. So whatever energy one body loses, the other one gains it. So, for example, that hot hand or that hand on a hot stove, whatever energy is being emitted by the stove is being directly absorbed into the hand. There is no energy loss per se. It's just simply being transferred directly from the surface to the hand. And the second law simply states that energy always transfers from the warmer to the cooler body, which makes sense. Energy would go from something that has a warmer or higher kinetic energy to something that has a lower or less kinetic energy. So that boils down just the simple laws of thermodynamics. I hope you guys didn't struggle with that too much. Not a whole lot of math with this part of the unit, but be ready because we will be moving on to something different here in 1 week's time. Have a great day, guys. We will talk to you later. Bye-bye.